All right, one more video for examples dealing with the fundamental theorem of calculus. These examples will be a little bit different than the ones you saw in the previous video, in that instead of just having your variable, x in most cases right here, we have a function right here, sine of x in this case. And you might wonder how that'll change things and if the answer will still be predictable. And the answer is, yeah, it'll still be predictable, but it'll change things quite a bit. Because if you go back to our original statement of the fundamental theorem of calculus, this guy right here, informally what it says is this integral and this derivative will kind of cancel out as long as this is your variable x. But if this is a function right here and you try going through these exact same steps that we did in this video, you'll see that things break down and we end up with a different answer than maybe you'd expect. That answer, that different answer that we get, will still be predictable. It just won't be the same answer that we've been getting. So let me show you how to go through the steps, and then we'll look at what the answer is. And then we'll learn how we could predict that answer from the very start, which is kind of nice to be able to predict the answer from the very start. It makes it easy to get the answer, and it's a good check. But again, just like in the previous videos, it's more the process than the result that I care about. I want you to be able to show all these steps. So suppose our function f of x is the definite integral from some constant, pi over 2 in this case, to a function, sine of x in this case, of this other function, t squared plus 3t plus 1. And what we're asked again is to find f prime of x. The steps we used in the previous video is first we rewrote this function f of x by using the evaluation theorem. And we're still going to do that. All right, we're still going to take the antiderivative of this guy. So 1/3 t to the third power is the antiderivative of this first term. And then 3/2 t squared is the antiderivative of the second term. And then my variable t is the antiderivative of this term. And I still need to evaluate that from pi over 2 up to sine of x. And evaluating this from pi over 2 to sine over x, nothing changes. So I'm still going to start by changing each of my variables, t in this case, into sine of x. And then from that, I'm going to subtract what I get when I change each of my variables into pi over 2's. And now what I have is an expression with a few extraneous parentheses that don't cause any harm of this function evaluated between these 2 points. That's this guy. I have a new way to write f of x. And just like we did in our previous examples, after we had a new way to write this function, I think in the previous examples I called it g of x, now I'm calling it f of x, it really doesn't matter. We can take the derivative and find f prime of x. All right, this is going to be a little bit more challenging, but I think it's a derivative that I can take. Let's look at this first term here. This 1/3 is just a constant, so we'll leave it alone. And then we'll take this 3, and we'll bring it down in front and use the power rule here. So the 3 and the 1/3 will go away, and I'll be left with sine of x squared, which you can write as sine squared x, by the way, but I'm writing it this way to try to make it really clear what I'm doing. But then I'm not done if I were taking the derivative of this. Right, I'd use the chain rule, so I'd have to multiply it by the derivative of the inside function, sine of x in this case. So there'd be a cosine of x right here. And then I'd do the same thing on the next term. I would take the derivative of this by leaving the 3/2 alone, bringing the 2 down in front. This 2 and this 2 will cancel, and I'll be left with 3 sine of x. But then I'm still not done. I have to multiply by the derivative of sine of x, which is cosine of x. And then finally on this last term, when I take the derivative of sine of x, it's just cosine of x. And then looking at this huge mess, you might think you have your work cut out for you, but really you don't, because this is just some number. I don't know what number it is, but I don't care what number it is, because the derivative of any constant is just 0. So what I get is f prime of x is equal to this thing. You might note that you have a cosine of x in all 3 terms. So you could factor out that cosine of x if you felt like it, and you could write this as sine squared x plus 3 sine of x plus 1. And you're like, yeah, I guess you could factor out a cosine of x. I wouldn't have thought to do that. And you don't have to. This is a perfectly acceptable answer up here. The only reason I took it one step further is I think this is a more predictable answer. Right? Because remember, in these fundamental theorem of calculus problems, we've always been able to predict what the answer will end up being. Maybe by writing in this way, we can kind of see what happened. Right? Our original function was t squared plus 3t plus 1. We're used to our answer being almost exactly the function you see here, except you change the variables into whatever variable you see here. So instead of my final answer being secant squared t, my final answer is secant squared x, which is what I wrote right here. Well, down here, that's almost what I did, right? I took this function right here, and my answer is almost this function. You might see some connections between this function and this final answer. The differences are 2. 1, I changed all of my variables into sine of x's. Right, so sine of x is what's being squared, and then 3 times sine of x, and then plus 1. You see all that right here. But then I'm not done. I have to multiply that entire thing by the derivative of sine of x. That's this cosine of x. When the cosine of x was distributed into all the other terms, it was hard to see the final form that my answer is going to take on. But the claim that I'm making is that you should be able to predict your answers on these questions just like you could predict your answers on the previous question. Anytime you're taking the derivative of something that's in this form, so it's the same as our fundamental theorem of calculus form, except you have a function here instead of a variable, you do the same thing you've been doing. You change all of these variables into whatever function this is right here, but then just remember to multiply that answer times the derivative of what you see here. I can write that more generally. Here's another formula that I suppose you could think of as a more general statement of the fundamental theorem of calculus. I don't know if it's even worth your time to like write this down or memorize it or anything. It might be easier to just kind of think about the steps that produce your answer. But let me talk you through what this is saying anyways. If you have this setup where some function, we'll typically call it g of x, although you see you don't have to call it g of x, we'll typically call it g of x, is equal to the definite integral from some constant up to no longer a variable, no longer the variable x, but now a function of x, h of x in this case, of some other function f of t. If you're in that case and you're asked to find g prime of x, if you want the derivative of this guy, well, the integral and the derivative don't quite just cancel each other out. What we have to do in this case is rewrite this function just like we've been doing, changing the variable into what used to be an x and now is an h of x. So what I'm saying is our answer won't quite be f of t, it'll be f of h of x. So you copy this function here and you change all the variables in that function to whatever you see up here. Function composition. But then you're not done. You still have to multiply by the derivative of this inside function here. Kind of looks like the chain rule, right? This isn't quite the statement of the chain rule, but it's kind of the same idea. Based on what you learned about the chain rule, if you're really good with the chain rule, you might be able to predict this. You might be like, yeah, this integral is going to cancel out with the derivative. So there's sort of the prime right here that canceled out because I had the integral. But then you got to leave the inside function alone and you're not done. You multiply by the derivative of the inside function. Maybe you can kind of see the chain rule going on here. Even if you can't, we saw the chain rule in action down here. Because this is a function and not a variable, I'm going to end up with a composition here, function composition. I'm going to end up with a function inside some other function. So when I take the derivative of that composite function, I'm going to have to use the chain rule because the chain rule is what I use for functions. To see if that made sense, see if you can predict the answer to this next question, and then we'll go through and actually solve it. Here's the question, the typical setup that we're used to. We have this function g of x, and it's the integral from some constant up to, no longer just a variable, but now a function of that variable, x to the fourth power, of something. And I'm asking you to find the derivative of this guy. Find g prime of x. So think about it. Do you know what this answer would end up being? Well, what we learned in the previous video is that we can almost just rewrite what you see here, except we have to change the variable from t to what's up here. And when what is up here is just an x, it's easy, you're done. But when what is up here is a function of x, you have to change all the t's into that function, x to the fourth, and then you're not done. You still have to multiply by the derivative of that x to the fourth. What I'm saying is I think this should end up being 1 over 1 plus x to the fourth squared. And yeah, that's equal to x to the eighth, and it would be a good idea to simplify that. But then you're not done. We'll multiply that by 4x cubed. Not to be too repetitive, but in addition to just coming up with the answer, I want you to be able to show these steps. Let's go through the steps. Step 1, let's use the evaluation theorem to rewrite this function g of x. If I want to use the evaluation theorem, I take the antiderivative of this thing right here. The antiderivative of this thing is arctangent of t. And then I evaluate that antiderivative from 10 to x to the fourth power. And that looks kind of weird, but it's not as bad as it seems. All you got to do is copy exactly what you see here, changing the t's first into x to the fourth, then into tens, and subtracting those two things. So I get the arctangent of x to the fourth power, and then I want to subtract from that the arctangent of 10. What I've done is I've used the evaluation theorem to rewrite g of x. Great, good work, but that's not what the question asked. It didn't say, tell me another way to write g of x. It said, what is g prime of x? So we got to take the derivative of this. But since we've done all this work, we can take the derivative. This is a form that we can take the derivative of, whereas this and this we're not. G prime of x is, let's see, what's the derivative of arctangent of x to the fourth? This is a fairly hard calculus 1 question, but maybe you can do it. See, I remember the derivative of arctangent of x was 1 over 1 plus x squared, but that's not what it's asking me for. It's asking me for the derivative of arctangent of x to the fourth, so I guess that would be 1 over 1 plus that thing squared, that thing being x to the fourth power. But then I got to remember I'm not done. I still have to multiply that by the derivative of x to the fourth, which is 4x cubed. And I'm still not done. I have to now take the derivative of this next term, which you're probably starting to see a pattern here. This is just a constant. I don't know what the constant is, but it's some sort of constant. And the derivative of that, any constant, is just 0. So what I get for g prime of x is this thing, which you could leave it this way if you wanted, or if you think that this is prettier, you could rewrite it in this form. I see advantages to both. I think this is a little bit prettier looking, but I think that this is easier to predict from the original question. So I think that this kind of shows more what's going on as you go through these steps. All right, here's a third example. In this example, I want to illustrate two additional things, both of which you've kind of seen before in the previous video, but now we want to examine them in the case that one of our bounds of integration is a function as opposed to just a variable. So suppose we're given this problem. The first thing you might notice is that the function here is kind of in the wrong spot. We're used to having that function up at the top of our definite integral. In fact, the formula that we kind of came up with that you really don't even need has that function explicitly placed up here at the top. And so you might wonder what happens when it's down at the bottom. Well, when it was just a variable down at the bottom, we just had to negate this thing. We'll see if that works here as well. The other issue that you might notice, and maybe it's not obvious, is that you don't know the antiderivative of tangent of t. You're like, yeah, I do. It's secant squared t, right? No, that's the derivative of tangent of t. The antiderivative, I don't believe you know that right now. I don't think you can come up with a function so that when you take the derivative of that function, you get tangent of t as your answer. There is a function, such a thing does exist. We'll learn how to come up with it in the very next section, in fact. Kind of interesting, kind of fun to come up with that. But right now, I don't think you know anything. When you take the derivative of it, gives you tangent of t. Uh-oh, that's problematic. How am I going to use the evaluation theorem if I can't take the antiderivative of this function? Well, we learned a trick in the last video where you do substitution. We're going to do that exact same trick here. Can't take the antiderivative of tangent of t. However, if we just call tangent of t little f of t, then it's super easy to take the antiderivative. It's just capital F of t. I don't want to get too far ahead of myself. The idea is if you do this substitution, then this original setup, instead of having a tangent of t right here, we have a little f of t right here. And the advantage to having a little f of t right here is now we can use the evaluation theorem. The evaluation theorem just says take the antiderivative of what you see here. It was impossible to do at this point in the class when that something was a tangent of t, but it's super easy when that something is a little f of t, because the antiderivative, by definition, is just capital F of t. Evaluating this is fairly easy. All I have to do is first change all the variables into 1s, and then change all the variables into e to the 2x, and then subtract those two guys. So the evaluation theorem tells me that this is equal to this down here, which is not my final answer because the question didn't ask me to rewrite g of x, it asked me to find g prime of x. So to get my answer, I have to take the derivative of this thing right here. And you might think that's going to be super hard, but I think it's doable. Let's take this first term, the derivative of capital F of 1. How am I going to do that? I don't know what capital F is. You don't need to know what capital F is. All right, without even knowing what capital F is, it's some function. You've changed all the variables into that function into the number 1. So it's equal to some number, some constant. You don't need to know which constant it is because you know that the derivative of any constant is just 0. What about the derivative of capital F of e to the 2x power? That's really hard because I don't know what capital F is. Right, but we do know what little f is, and by definition, capital F is the antiderivative of little f, therefore little f is the derivative of capital F. So if I want the derivative of this thing, I can just use what I know about little f of x. But wait, there's more. Right? This is a composite of two functions. It's some unknown function with some other function inside of it. Remember what you did in Calc 1 when you had a function inside of another function? First, you took the derivative of the outside function, and you left the inside one completely alone. So maybe little f of e to the 2x power. And then you still weren't done. You had to multiply by the derivative of the inside function. So the derivative of e to the 2x is e to the 2x times 2. Another chain rule going on there. Hopefully you're comfortable with the derivative of e to the 2x being e to the 2x times 2. So wait, this is my answer? And not quite, but almost. Little f we shouldn't leave in our final answer because little f is something we made up in the problem. right? There was no little f in this problem to begin with. Little f is something we put in as a substitution, but it's already done its work. It changed into its antiderivative and then back into itself. Now we can substitute back in and change little f of e to the 2x into tangent of e to the 2x. And for our final answer, we get the negative of the tangent of e to the 2x times e to the 2x times 2, which is a perfectly acceptable way to leave your final answer, although I think it's a little bit prettier to write things in this order. Although you could argue that this order is preferable because it more clearly illustrates that all we're doing is we're rewriting the function that we see here with this in place of the variable, and then we're multiplying by the derivative of this. And oh, because the order of integration was weird, it was the opposite of what I expected, I need a negative in front of the whole thing. I need to negate this to reverse these bounds of integration.